In this video, I want to give you just a brief introduction and explanation about how light or electromagnetic radiation and electrons are related. So at the beginning of the year, you might have done a flame test lab where you put certain elements in the flame of a Bunsen burner. That heat got the electrons excited, and then when those electrons relaxed, they gave off certain colors of light, and we could use those colors to determine what the element sample was. So oftentimes we explain that process through one of these old-fashioned Bohr models. This is probably that model that you learned about in 8th grade. So these are the various rings or energy levels. Here's the nucleus, energy level 1, 2, 3, 4, 5, 6, 7, and so forth. So when you put that element or atom in the Bunsen burner, the electron gets excited. And then when it falls back down to a lower energy level, it gives off a specific amount of energy, a quanta of energy, and that amount of energy is associated with a very specific wavelength. And you can use your light equations to do that. Energy of that photon is equal to h, Planck's constant, times c, speed of light, divided by lambda, which is wavelength. So those energy transitions give us these very specific colors of light down here. The problem with this explanation is that the Bohr model doesn't really do a great job of explaining the data. The Bohr model, even Bohr knew it was kind of lacking in detail and accuracy. It really only explained hydrogen, which has one electron. So the question is, how do we explain this absorption of energy and then release of energy in the form of light using what we now know about electrons, SPDF orbitals? So there's a really great website out there called Beyond Bohr, and they're trying to explain quantum theory a little bit better using our understanding of electron orbitals. So in this little demonstration, I'm going to show you what happens when a 1s orbital electron absorbs energy and goes to a 2p orbital, and then backwards. So they did a great job programming this little animation here. And what's going to happen is, okay, this is the 1s orbital. It's a spherical orbital. Here's the nucleus. And throughout the number of oscillations here, throughout the video, you're going to see light going in and out of this atom. And that light has a specific frequency. And in this case, the frequency of the light, which again is c equals lambda nu, that frequency would be the frequency of the light, is in perfect relationship to the frequency of this s orbital. So that's why it's a 1-to-1 ratio. And you'll see through that constructive interference how that s orbital is transformed to a 2p orbital. So you can see this shape right here looks exactly like the p orbitals we've been talking about in class. And again, this is a much more accurate way of representing what's actually happening in the atom. Rather than thinking of an electron going from ring 1 to ring 2, you can think of that light exciting that wave and causing some constructive interference, causing that s orbital to be elevated to a 2p orbital. The same thing happens when that electron then loses energy. We can go in reverse here, and as that electron loses energy, it's going to give off a certain amount of energy in the form of light, and those would be the colors that we see in the Bunsen burner or when doing the emission light bulbs, the emission light spectra. Those are those various colored lines that we see. So again, this is a much more accurate representation of what's actually happening. You can see that this ratio of frequency of the light to the frequency of the electron has to be in perfect sync, even if it's off by just a fraction of like a percent here. So this is like 95% the frequency of the electron orbital. I'll try to speed it up a little bit here. Oops, I want to go in the forward direction. There we go. you can kind of see there it gets a little bit out of sync. It's not vibrating at that perfect frequency. So here would be an unsuccessful transformation from the 1s to the 2p. That would not be a good electron transition. And let's say we have lots of frequency, lots of energy in that light. Sometimes you might think more is better, more energy, more frequency. Maybe that would really get that electron to transition well. Well, let's try it. There we go. You can see that light is vibrating so much that it's kind of canceling out the vibration of the s orbital, and we get an unsuccessful transition there. And then we can go ahead and scale it up to, let's say, a 2p orbital going to a 3d orbital. So here's a 2p orbital going in the y direction, and notice how the frequency to resonant frequency is in perfect 1-to-1 ratio. Speed it up a little bit here. Notice how that light and the electron orbitals are in perfect sync with each other. You got a lot of great distortion there. And by the end, we've turned that 2py orbital into a 3d xy orbital. So again, a much more accurate representation. Rather than saying the electron goes from ring 2 to ring 3, you're really talking about vibrations of waves, and that 2py or that 2p orbital got distorted into a 3d orbital. And then when that electron goes to lose energy, same thing happens in reverse. It's going to give off a specific amount of energy associated with a certain wavelength. And now we're back to the 2py orbital. So hopefully that gives you a much better understanding. We know the Bohr model's not great. We try to use it because it's kind of simple. It's great for 8th grade, and even chemistry teachers in high school and college use it. But I think it's time to kind of move past that simple wrong understanding and understand what we're actually talking about in terms of what we actually discuss in class, the s, p, d, f orbitals. All right, have a great day.